Welcome to Empowered Learning. This video will be about the concept of what a series is, and we're going to unpack several things that we use series for. So specifically, we're first going to talk about the vocabulary around what a series is. Of course, we'll define it, and we'll contrast that with what a sequence is, as well as tell the similarities of how a sequence and a series are related to each other. We'll also talk about forming a sequence out of terms of a series. Okay? We're also going to study three very important series types. The first will be a geometric series. The next will be a harmonic series. And the third will be a telescoping series. Finally, we're going to look at some series and determine whether these series will converge upon some number or not. And then we're going to use the application of series, which is we're going to take numbers that are decimal numbers that are either decimal numbers that are repeating, and we're going to rewrite those as fractions. And so one of the things that we know from the definition of a rational number is that rational number is a decimal number that is either terminating or repeating. Of course, the terminating numbers are very easy to turn into a fraction, but the ones that are repeating, not so much. And so we can actually use geometric series in this case to be able to do that. All right, so let's go ahead and get started here. So first things first, we want to recall from the video on sequences that I did, if you watch that, that of course that a sequence is a function whose domain is the set of natural numbers. Okay, and again, we want to think about a sequence as f of n versus a regular continuous function f of x, where f of x is considered to be any real number, depending upon what the domain of the function is, whereas for a sequence, that n is solely the natural numbers. Okay, and again, for the sequence, we just use n really as a way to keep count of what particular number is in the particular sequence. Let's say it's the first number, second number, third number, so on and so forth. So that is one of the functions of what n is. But of course, we can also express a sequence algebraically to be able to calculate what each number would be. So we want to recall that. Now we have an infinite series of a sequence is just going to be the sum of all the terms that's in that sequence. So if I was to essentially add all these numbers up here and I get an answer, then that would actually be the sum of that particular sequence. And the process of actually adding up the infinite amount of these numbers that it would actually be called a sequence. And of course, if we wanted to express that in summation form, it would just look like this, where based upon how the sequence could be defined algebraically, that would be what a sub n would be. And of course, we'll start at n equals 1 and go on to infinity. If we wanted to do it very shorthand, we would just write it like this. Now, sometimes instead of us knowing what the infinite series is, or put another way, instead of us wanting to know, well, what is going to be the sum of all the numbers in the sequence if it goes on to infinity, we're sometimes just interested in the first n terms. So in other words, if we use this, if you go back to the video that I talked about on sequences, one of the things I told you that we use sequences in series for is to be able to express a function that does not have a elementary function antiderivative as an approximating polynomial. And if we look at it in that context, we realize here that, hey, I may not want a polynomial that has a million terms in it to be able to approximate that function that I'm looking for to do the antiderivative of, I may just want the first 100 terms, and that may be good enough for me to get an approximation that's good enough for what it is I need to use it for. Okay, and so that would be an application of why sometimes we would want just the first n terms instead of allowing n to go to infinity all the time. Okay, so sometimes we're only interested in the sum of the first n terms of a sequence instead of the sum of all the terms, and now you got an explanation or an example of why that is. So if we let s sub n be the nth term of that sequence, then of course we see here that we could start to add up what the series, or the terms of the series would be there. And so here we see that if we had s sub 1, then that's going to be the nth term, okay, when n is 1. Here, when s sub 2, that's just going to be the nth term of the sequence, of course, when we add them up. So here, remember again that we're interested in the sum of the first n terms, okay, not just what the nth term is, okay. So that's why we have s here instead of like how we had up here, have the a. So this is different. So I want to make sure that that's clear. So we're interested in the sum of the first n terms. So if we just want the first term, then it's this. So the sum of the first 2 terms, it'll be this. Sum of the first 3 terms, it'll be a sub 1 plus a sub 2 plus a sub 3. And of course, we want the sum of the first n terms. It will look a sub 1 plus a sub 2, keep on going all the way to a sub n. And so what we call these is the partial sums of this particular sequence. Okay, so we know that a sub n is the algebraic representation of a sequence or a list of numbers. We know that if we list those numbers out, it looks like this: the a1, a2, a3, a4, okay, so on and so forth. And I'll erase these equal signs here, kind of make my point. Yep, so that's what those numbers are here. And then, of course, if we add up all those numbers, the a sub 1, a sub 2, then what that would actually be is a series, because it's the sum of all the numbers in the sequence. But then if we wanted to break it out and say, all right, well, I just want partial sums, then what the list of partial sums would be, as we say, I want the sum of the first 1 term, 2 terms, 3 terms, 4 terms, that will be called a sequence of partial sums. Okay, or as I put it here, these are going to be the partial sums of the sequence, and we can actually put a sequence together itself from this particular list. So in other words, we could have something that looks like this, to where let's say we have a sequence of numbers, so S1, S2, so on and so forth here. Let's try to get that pen writing correctly. So S1, S2, S3, so on and so forth. And that would actually be a sequence as well, because again, it is just a list of numbers. So the sequence of partial sums here, of course, is a sequence. And the whole point here is that we can take partial sums and actually form a sequence out of that. So to summarize here, we know that we have an arbitrary sequence. And of course, that's just a list of numbers. The infinite series of this sequence is just basically adding up all these numbers in the sequence together. Okay. Now, if we wanted to look at the partial sums of the sequence, meaning S1 would be the sum first term, S2 would be the sum of the first two terms, S3 would be the sum of the first three terms, so on and so forth. If we took this list of numbers that we had here, that would also create another sequence as well if we just looked at the list of numbers. Okay, so we have a sequence, we have an infinite series. If we just wanted in terms of that, then of course we would have a finite series of length n, and then we have a sequence that can be formed by the partial sums itself. Okay, so those are the three main things that we need to keep in mind: what a sequence is, what an infinite series is, and I'm also going to throw finite series is, and then what is going to be the sequence of partial sums. All right, so now that we've established this vocabulary and some of the definitions about series, now what we want to do is give a formal definition for partial sums of a series, as well as defining the convergence and divergence properties for a sequence of partial sums. Okay, and afterwards we're going to talk about geometric series and harmonic series. All right, so definition: convergence and divergence of an infinite series. So if we're given a series, and this is just a general way to state it, and remember that this series comes from the sequence that's formed by whatever this a sub n is. So the list of numbers that comes about from that, if we add them up, this is what we get. And we know that S sub n is going to be the sequence of nth partial sums from this particular list. And that is expressed this way. Okay, so if we have all of that, then the series, so this series here that we've been talking about, is called convergent if the sequence of partial sums, so there's this sequence here that's made up by adding the first term, and then the next is going to be the sum of the first two terms, next sum of the first three terms. If that particular sequence that's made up of these partial sums is convergent, and another way that we actually say that is that the limit of this sequence of partial sums actually exists. So I'll read that again. So we have this series here is called convergent, meaning that if we add up the numbers in this particular series here, we add up all these numbers, we know that these numbers will add up to converge upon some single number if we know that the sequence of partial sums is convergent. Okay, and we could take out, just for now, I'm going to take out the partial sums part, and I'll just read it this way. The series is called convergent if we have this special sequence that is convergent. And if you remember the sequence video that I recorded, you'll know that how we tell if a sequence is going to converge upon some number or not is that the limit of the algebraic form of that sequence had to exist. Okay, so it had to be converged upon some number here. So a good example of that, and we'll actually see this later, is let's say a sub n is equal to 1 over n squared. Okay, so let's say that. So if I wanted to form a sequence of numbers, it'd be like this. Now, because the limit as n approaches infinity of 1 over n squared here would just basically be 1 over infinity squared, which approaches 0, and 0 is a real number, we know that this particular sequence of numbers here will converge. or we say that it is convergent. Okay, so what I'm demonstrating here is this part of it. And so what we're trying to do is find a way to figure out if a series is going to converge upon some number by not having to actually add up all the numbers. Okay, so we kind of take a quicker way around that by saying, well, hey, let's see the sequence of partial sums that particular series could come up with. And if the sequence of partial sums is convergent, then that means that the series for which that sequence of partial sums actually came from, it's also going to be convergent. Okay, and so specifically, if we know that a infinite series is convergent, then we write its sum as S. So here, get my pen working again here. So we could express it this way, and of course n is going to infinity here. So that's why it will still be an infinite series, and we just say that the sum of that series is S. Of course, we could name it anything that we want, but just in general here, we'll just call it S. And we'll say that S is going to be called the sum of the series of this particular sequence. And if it's convergent, then of course it's going to converge upon whatever number this is. Now, if the infinite series is not convergent, then of course we call it divergent. Now, what does that mean? So if it's divergent, that means it's either going to grow out of control positively, meaning going up to positive infinity. It's going to grow out of control negatively, which means it's going to go down to negative infinity. Or you may have a situation where you're trying to add up these numbers and it's just kind of going back and forth. So let's say if I had a sequence that kind of just went back and forth, back and forth, back and forth the whole time, if I added up those numbers, not much is going to change in the fact that it's not going to go down to a certain number. It's not going to go up to a certain number. It's just going to keep oscillating or vacillating back and forth, kind of going nowhere. And so in that case, that is also a situation where we would call the series being divergent. All right, so all that to say in summary, that if we want to see if an infinite series is convergent, what we're going to do is look at its sequence of partial sums and see, is that sequence of partial sums going to be convergent? And we do that by expressing the sequence of partial sums in algebraic form in terms of n and just taking the limit of that. Okay, and so we'll get more practice with actually applying that later. Right now, though, what we want to do is illuminate some important series or infinite series that will be important to us moving forward here. And so we have an example of an important series that is convergent under some conditions and one that is divergent under a lot of conditions. So here the geometric series is probably the most popular one of the ones that's used the most. And in general, of course, we call it a geometric series because it comes from a geometric sequence. Okay, and of course, here we know, for example, if I had the sequence, let's say 1, 3, 9, 27, so on and so forth, then we could characterize this as being this particular sequence here. So we can characterize this by being this particular sequence. Okay. Of course, if I start off with n equals 1, 1 minus 1 is 0, 3 raised to the 0 is 1. And of course, if n is 2, 2 minus 1 is 1, 3 raised to the 1 is 3, so on and so forth. So my point here is that this is an example of a geometric series, and a geometric sequence, because the ratio in between any two numbers here is always the same. In this case, it is 3. And of course, we have geometric series come from geometric sequences. Okay. And so that's the motivation for this particular series. Now, of course, if I wanted to add up, let's say, all the numbers in this particular sequence here, then it would look something like this, where my A would just be 3. Now, we know that the geometric series is convergent if this value of R here, and I think I said A has to be 3 here, but really I meant R has to be 3 here. So if I misspoke there, I apologize. So here the series is going to be convergent if R is going to be in between -1 and 1. Okay. Put another way, we want to make sure that R is a proper fraction. Okay. And we know that if R, or the common ratio, is a proper fraction, then we know as we take that proper fraction and raise it to higher and higher powers, the numbers are going to get lower and lower and lower, okay, as a result. So if our common ratio is in between -1 to 1, then it's going to be convergent. Otherwise, we're going to have a divergent series, okay? And we know that whenever our common ratio here is in between -1 to 1, we know that the sum of our series will always equal to whatever this constant A is divided by 1 minus R. And that will be what we call the sum. Of course, that's always true. Okay? So we see here that the geometric series is convergent under the special condition here that the common ratio has to be one that's in between -1 and 1. Now, the harmonic series is always divergent, okay, no matter what. And so the harmonic series is just the sum of all the numbers 1 divided by n, where n is equal to 1 on to infinity. Okay. Now, it seems like that would not be the case here because of the fact that, of course, 1 divided by n, as n got bigger and bigger, 1 divided by n would get smaller and smaller. But it turns out that for this particular series, these numbers here do not decrease. Well, let's say the numbers in the sequence do not decrease fast enough for the harmonic series to actually converge upon some number. Okay, so the harmonic sequence, or these list of numbers here, this sequence will converge, and it'll actually converge upon the number 0. Okay, so this sequence is convergent, but the series is not, and that's an important thing for us to understand. So the harmonic sequence is a convergent sequence, meaning that the more numbers we list, if we go to infinity, we know that theoretically that last number would be 0, and that is what that sequence will converge upon. However, in the harmonic series, we're taking all the numbers in that list and we're just adding them up. And of course, yes, as we add more numbers to the previous ones, yes, what we're going to be adding is going to be smaller and smaller each time, but it's not going to be small enough, fast enough for this particular series to be able to converge upon some number. Okay, so that's one of the things that we need to make sure that we hold true on. All right, so to take a look at how we would use this in a very simple example here, let's determine whether the following geometric series converge or not. So we're going to see a couple of them. If it's convergent, we want to find its sum by taking the limit as n approaches infinity of the nth term of the sequence of partial sums. Okay, unless we have a situation where, of course, since we're talking about geometric series, we kind of already know what the answer is going to be, and that sum in this case is just going to be a divided by 1 minus r. If, of course, r is in between -1 and 1. Okay. All right, so in this case, we have the sum of a list of numbers. And of course, that list of numbers is 1. So let's try to get this working here. All right, so we got 1, and then 0.4, and then 0.16, so on and so forth. And of course, if we were to rewrite this is 4/10, 16 100ths, 64 1,000ths, and of course here this is 4/10 for this one. We know that 16 100ths is the same as 4/10 raised to the 2, and 64 1,000ths is the same as 4/10 raised to the 3. So that's why you see that there. And we see that the one thing that is in common is this common ratio here of 4/10. And of course, even with 1 here, this could be looked at as 4 divided by 10 raised to the 0. Okay. Now, of course, 4/10 reduces to 2/5, and thus we see that we could rewrite our series here that we're talking about in terms of A. And of course, A in this case is going to be 1. R is going to be 2/5. So since 2/5 is a number strictly in between -1 and 1, we know that this geometric series will end up converging. And so what this means for us here is that this infinite series that could be expressed this way, where of course this is A, that's R, is just going to be this value 1 here. So this value 1 over 1 minus 2/5. And for some reason I have an 11 there, and I don't know why that is, but we're going to go ahead and change that now. All right, so we went ahead and we fixed that. So now we see, and let me change these colors back to what they're supposed to be here. All right, so now we see that we just have 1 divided by 1 minus 2/5, which is 1 over 3/5, which is the same as 5/3. So we see that that ends up being our final answer there. All right, so for our next example, we have the series written in its compact form, and what we need to do is figure out, is this going to be a geometric series that converges or diverges? So the first thing here that we can note is, let's just deal with what we have here on the inside of the summation operator. So that's 10 raised to the n divided by minus 9 raised to the n minus 1. And of course, we could rewrite this as 10 raised to the n over minus 9 raised to the n times minus 9 raised to the minus 1. And of course, this 10 divided by n divided by 9, negative 9 raised to the n, we could just look at this as 10 over 9, or 10 over negative 9 raised to the n. So here we have understood 1 divided by a negative 9 raised to the negative 1. And of course, this is just like saying, what is the reciprocal of negative 9? And the reciprocal of negative 9, sorry, the reciprocal of negative 1/9. Yeah. So I'll just go ahead and write it out. So this actually ends up looking like this. Right. And so now from there, we know that the reciprocal of a negative 1/9 is a negative 9. And also here, since I have 10 divided by a negative 9, I could rewrite what's on the inside of there as a negative 1 times positive 10 divided by 9 raised to the n. And so this now would be a negative 9 times a negative 1 raised to the n times this. Okay. Now, in writing it out this way, one of the things that we see here is that this would actually end up being what we call a alternating series because of this part here. But for the purposes of this problem, the main thing that we're concerned about is this value here, and that represents what our R actually is. Okay. Now, if we kept this negative 1 raised to the n on the inside there, you would just essentially have this, and this number here still would be considered to be R. And so our goal here is that we know that this is a geometric series. So what we want to do is compare that to what we have here. And so if we compare basically a raised to the r, a times r raised to n minus 1 to what we have going on here, which is the minus 9, negative 10 over 9 raised to the n, then of course negative 9 is the a, and negative 10 over 9 is the r. And since r is outside, so it's not a member of this set of values in between negative 1 to 1, because r is this value here, this implies that this particular series will diverge. So let's say geometric series diverges. Okay. All right, so we see an example of a geometric series that will converge, example of a geometric series that will diverge. Okay, so this will conclude the part 1 video for the concept and discussion on series. In the part 2 video, I'm going to start off going over some basic facts that comes as a result of us actually defining what a series is and sort of laying the ground rules for what it means for a series to be convergent versus a series to be divergent, and of course illuminating the harmonic series and the geometric series. So we're going to talk about some basic facts that go along with that, and then we're going to do some other examples to where we determine whether a series converges or diverges, and we're also going to talk about the telescoping type of series that come about in doing some of these problems in that second video as well. So hope to see you there.